So good morning and welcome everyone. This is discussing heat and thermodynamics lecture number 3. Up till now, what we have done is just gone through the basic definitions of things, and we have been wandering here and there. As soon as something comes up, we start discussing it. In the last class. We had discussed a lot about state variables and state functions and path independence and path dependence, right? Do you all remember this? What are state functions, state variables? Internal energy is a state variable and therefore it does not depend on path. Whereas work and heat given to anything, heat given and taken out depends on path. It is not a state function. We remember this?
Yes, sir.
Okay, then in today's class, we'll go ahead and we will start with the first thing that we must understand in this chapter. I mean, the entire thermodynamics can be divided into various sections or various subtopics. The first subtopic is thermometry, then it is calorimetry, then it is thermal expansion, then it is heat transfer, then there is specific heats, and then there is a first law of thermodynamics. So we will be doing them one by one, and the first thing that we start with, we have started already, but the first thing that we start with is known as thermometry. Do you understand what is thermometry? Have you heard the term thermometry? Anyone?
No, but
No, but what? You not heard the term thermometry? No, may not be necessary that someone would have called it thermometry. Thermo means temperature, thermo, temperature, heat. Metry always means the measurement, right? Calorimetry means measurement of calories. Thermometry means measurement of temperature. So thermometer. So basically, thermometry means the measurement of temperature, right? Now let us start with this measurement of temperature and how am I going to do it? Let us start first with the definition of temperature. I think we have already defined temperature. Yes or no?
Yes, sir.
What is temperature? Let me remind you. You remind me. What is temperature?
Is the hotness,
Temperature is the degree of
hotness and
hotness
coldness of a
or
body.
the degree of coldness of a body. It has got nothing to do with heat. Remember, where does heat flow? Yes, heat does flow because of temperature difference, and it is always flowing from a point of higher temperature to a point of lower temperature. It is same as understanding something because of potential energy will always go from higher point to lower point. In fact, current is also similar. Whenever we talk about the conventional direction of current, what is conventional direction of current? Entire physics is us. We have to revise the entire physics. What is the conventional direction of current? No one knows it?
Positive to negative.
Positive to negative. I don't understand that. Positive to negative. I don't understand it. Can you elaborate further? What is the I mean, electric current is already covered, right? With other in the other physics class. Yes or no?
Higher potential to lower potential.
Yes, that is better. From higher potential to lower potential. What do you mean by conventional direction? I use the word conventional direction. What do you mean by that? Heard the term conventional direction of current? No. No, no? Have you heard the term conventional direction of current? Either you have heard it or you have not heard it. Not, I'm not getting any response, so I'll assume that you have not heard it. Conventional direction now. Whenever we talk about current, when you say current is flowing in a wire, what actually are flowing there?
Electrons.
Electrons.
Free electrons.
Yes, free electrons are flowing there. Correct. With a velocity which is known as
Velocity.
drift velocity. Beta, drift velocity. Drift. You just probably read it maybe 10-15 days before. You can't forget this. It's known as a drift velocity. Okay. So electrons are flowing. Actually, electrons are flowing. Where do electrons flow? From where to where do the electrons flow?
Lower potential to higher potential.
Yes, electrons flow from lower potential to higher potential. So actually, in a circuit, the current is the flow of electrons. And they are flowing from lower potential to higher potential. But whenever we talk about the direction of current, we say conventional direction of current. Conventional direction of current stands for the direction of flow of positive charges. But we now know that positive charges actually do not flow. Protons do not flow actually. It's electrons that flow. But still we think it as the flow of positive charges, and therefore we call this direction as the conventional direction of current, which is exactly opposite to the actual direction of current. Now this actual direction of current, or we call it electronic or electrical direction of current, is the direction of flow of the real current electrons, and it is from lower potential to higher potential. The current actually flows from lower to higher, but we take it from higher to lower, and that is why we call it conventional direction of current. Do we understand this now? Am I clear with this point? Can I have some raised hand that we understand this?
Yes, sir.
So everyone in the class, I don't see any raised hands.
Yes, sir.
What's happening here? Yes, everyone understand this? Please raise your hands in the class.
Sir.
I only see boys raising their hands. What about girls? Do you understand this? Okay. Just raise your hands. I don't think that will create a lot of trouble to you. It will be a good exercise that you raise your hands. Okay. Now, why I brought current here, or for that example, potential energy, because we'll be using a lot of concepts that you have learned in current in the coming chapters. Because we are going to treat heat, the flow of heat, or the rate at which heat flows, dq by dt, the rate at which heat flows, dq by dt, sometimes I will call it dh or h, or sometimes I will call it IH. What do you mean by IH now? That is the reason that you must remember.
Heat current.
Yes, heat current. We call it, we can think of heat as current because heat and current are, heat and electric current are, can be considered as working in the same way. And that is why electric current. So if you have done electric current previously, heat current or conduction becomes very easy for you. Similarly, the other way around. So we will be using it again, and I will be telling you what I know about it. Okay. Then two bodies are said to be in thermal equilibrium. We have already understood the term thermal equilibrium. When no heat flows from one body to the other body, that is when the bodies are at the same temperature. I have discussed this with you. Okay, temperature is one of the 7 fundamental units. All of us know this. It is a scalar quantity. SI unit is Kelvin. We'll talk about the various units just now. When heat is given to a body and the state does not change, the temperature of the body rises, and if the heat is taken from a body, its temperature falls. Heat can be regarded as the effect. Temperature can be regarded as the effect of cause of flow of heat. Do we understand this?
Yes.
Heat flows from higher to lower temperatures. So it's as simple as that. Now, when the state does not change, such heat is known as specific heat. Have you heard the word specific heat? We will be encountering this term very soon. Have you heard the term specific heat?
Yes, sir.
Yes. And when the temperature and when the state changes, the heat given or taken or absorbed in that process is known as,
Again, sir.
when you are giving heat to a body and the temperature changes, we call that heat as specific heat. So here the heat is known as specific heat. But when the body is at its melting point or boiling point, and we give heat to the body or extract heat from it, the temperature does not change. The state of the body changes. That heat is known as
Latent heat.
latent heat. Okay, so we'll be doing all these heat very soon. According to the kinetic theory of gases, temperature, the two types of properties of a gas, one is known as macroscopic and the other one is known as microscopic. Microscopic, that they are very small properties which actually cannot be seen. Macroscopic property of a gas are properties which can be measured and which you can imagine. Now, what are examples of macroscopic property of gas? Heard the term macroscopic property? May not have, but you know what are the macroscopic properties of a gas? Properties of a gas, or quantities of a gas, quantities that can be measured probably. You can call them as macroscopic properties of a gas. Can you name some macroscopic properties? One example is given here.
Temperature, value,
Temperature,
pressure, volume.
temperature, pressure, volume. All these are macroscopic, larger properties of gas. Now this temperature, pressure and volume. Why does pressure come in a gas chamber? If you have gas inside a cylinder, inside a chamber, inside a room, inside a box, why does it create pressure? All those things. The macroscopic properties come from the microscopic properties of the gas, and that is given by another topic which I missed in my list. KTG. Do you know what is KTG?
Gases.
Kinetic theory of gases. This theory tells us why these macroscopic properties come because of these microscopic properties, and this temperature is basically coming because of this temperature, and this pressure is coming because of, and they're related to each other because of this kinetic energy of these molecules, these gas molecules. A very large number of gas molecules are contained even in a very small 1 mole of gas, and 1 mole of gas is very small, 6.023 into something. And these molecules and these atoms molecules are constantly in motion, so they have transitional energy, they have kinetic energy, they also have potential energies, and we will understand about all those energies in the topic of internal energy of a gas. I'll discuss these. In kinetic theory of gases, I will discuss this. I hope this is clear to all and you are writing the important points here. Yes or no?
Yes, sir.
Have you got this sheet with you?
No.
Did you get it? No. Okay, I think I have sent it. Probably I'll check it, and probably I will. If I have not sent it, I'll send it. I'm just getting too much absorbed. Okay. You know that the temperature is directly proportional. This actually the other way around. The kinetic energy of the gas molecules is proportional to the temperature. Have you heard this? We will be discussing this in great details in the chapter of kinetic theory of gases. The lowest possible temperature of a gas is how much? 0 Kelvin. We have not achieved that. We have come very close to that. Highest possible temperature is about 10 raised to power 8 Kelvin that we have achieved in laboratory, and the lowest is always 10 raised to, is almost 10 raised to power minus 8 Kelvin. This is just for theoretical process. Branch of physics dealing with the production and management of is known as cryogenics, and the higher side is known as pyrometry. This is just for research purpose. Temperature of this, temperature of that, of no use. This is just for bringing up the topic as such. How much the temperature of this? No one is going to ask you this. Forget about this. Now the next thing that we have to understand is the scales of temperature. Do you understand the scales of temperature?
Yes, sir.
How do we measure temperature? How do we measure temperature? Now, if you are a scientist, if you are there, and let us see that no one else has created any device that can measure temperature. Any device that measures temperature is known as what? Thermometer, right? Thermometer is a device that can measure temperature. Now, you are the first one in this universe, or not in this universe, maybe there are much more advanced civilizations. You are first on this planet, and now you somehow want to measure the temperature of a body. You can touch it and feel it, and okay, this is hotter, this is colder, but that will not give you a precise measure of how much the temperature is. The first person on this planet, and you want to devise something known as a temperature scale or a thermometer. How do you do it? How do you devise a thermometer? How do you manufacture or measure or make a thermometer? Tell me. Now, you must have heard about this. The other thing, the only thing is you might not recollect it. That is why I'm here. How do you make a thermometer? Girls don't speak in this class.
Sir?
Girls don't speak in this class. I mean, we are living in a democracy, right? And everyone has this, should I say, fundamental right of speech. Anyways, you don't want to utilize that right. It's up to you. This is democracy. This is not Nazism that I am Hitler and you are Nazis. Okay. How do I create a thermometer? I'm the first person on earth. How do I create a thermometer? I'm giving a chance to become the inventor of a thermometer. How do you invent a thermometer? With all the knowledge that you have, forget about the first person who did it.
First we fix the
How do you, with your present knowledge, create a thermometer? Yes. Tell me. I'm not able to hear. Are you speaking, bacha?
Yes, sir. I'm speaking. Are you not?
No, I was
Is
not
it
able to hear anything. Yes, tell me.
first we take lower point and upper point.
No. You're missing the main point. Why lower and upper point? I don't understand. Upper and lower point of what?
Fixed points up. Yeah.
What fixed
And
points? You're the first person in this on this planet that you are going to invent a thermometer of your own. How do you create a thermometer? On what principles do you create a thermometer? What do you observe in this universe that motivates you or tells you, now this is how a thermometer should be built? Yes. There are no wrong answers, there are no right answers. Everything is about the idea. If you understand the idea, everything becomes simple. Yes. Tell me, how do I create a thermometer? But please speak louder. Let me increase the volume here. I think there is a problem with the volume somehow.
0.9.
Just give me a moment. Let me increase the volume from here. Speaker, dum. Yes, now speak. Bol bacha.
0.10 steam point.
0 point and steam point. You're still not getting my point, bacha. I touch something. I feel very hot. I touch something is very cold. Then I observe something. And that gets me, okay, this is how I can use this thing to create a thermometer, to create a temperature scale. 0 point and freezing point and melting point and boiling point comes afterwards. We observe and we see something happening, and that prompts us that, I can use this to create a thermometer. What do I use to create a thermometer? Okay, maybe my question is not correct and you are not able to absorb what I'm saying. As human beings, we observe, and we observe that something changes when temperature changes, when things are hotter and when things are colder. something changes in them.
Mercury level.
What?
Mercury level increases.
Sorry, please speak louder. Not able to hear. Was something wrong with my microphone?
Mercury level increases while other
Level increases. Now we are getting somewhere
temperature
here.
increases, mercury level increases.
Just a minute. I'll just do something. And I will do this. Probably I'll be able to hear you. Now speak.
Mercury level increases while temperature increases.
Mercury level increases when temperature increases. Now we are coming somewhere. That means what we are going to talk about here. Still, my voice is not good enough. I think your microphone is there, or your speaker volume, the microphone volume is low. I think the microphone volume is low. Okay, what we have observed in nature is that when temperature changes, certain physical properties of certain bodies change. For example, if I give an example, what are the physical properties or the physical quantities that can change when temperature changes? And we have seen it in real life. What? What all properties change? Volume of a liquid, it changes. Yes or no?
Yes, sir.
You've seen water or milk boiling. It boils, ooh, the volume increases. When it cools down, the volume decreases. So volume of a liquid can be used depending on how hot or how hot the body is, the volume is more. So I can use volume of a liquid to somehow create a temperature scale. What else can I use? What else can I use? Pressure of a gas. Pressure changes on change of temperature, yes or no?
Yes, sir.
Yes.
Yes.
Pressure is actually what we have seen, what we now know with the present knowledge. They might not have known it. And that is how they created the temperature scale, and that is how they probably got that ideal gas equation as well. They found out at very low pressures and temperatures, pressure is directly proportional to temperature, yes or no?
Yes, sir.
Temperature increases, pressure increases, and that thing can be used. Oh, if the pressure is more, then the temperature is more. If I can measure pressure, I can create a temperature scale. Idea. An idea can change your life. What else changes when the temperature of something changes? I've talked, no, the clue is here. I've talked about a liquid. I've talked about a gas. The only state remains is the solid state. Obviously, the volume of solid also changes, but the change is very, very small, and it's very hard to make it very large. See, when there is mercury in a column, the change in volume is very high. We can predict the change. We can see the change actually happening right in front of our eyes. But for a solid body, the change is not that much. But there's one thing that drastically changes in a solid body, and that is used, that can be used, that is used to find out the temperature or to make a temperature scale. What is the third thing? Tell me. And you have just done it. You've just done it. We discussed electric current as well. It comes from electric current. What is that thing that changes when temperature changes? Fast, fast, fast. Resistance of a wire. Heard about this term?
Yes, sir.
Resistance of a wire changes. The temperature increases, resistance increases. And it is fairly directly proportional to each other. So these are the three quantities that I have found out, and I can use any of these three quantities to create a temperature scale. But the problem is, what do I call what temperature? What do I call what temperature? Which temperature is what? It is very hot. What do I call it? This is very cold. So what do I call it? I now know how to create a temperature scale. I have some physical property that can be used. But how do I give it a value? So now we have different types of temperature scale. I hope you got this idea how these temperature scales are created. We are using physical properties that change when temperature changes. Thermal expansion, that is the next topic that will come just after this, after we understand how temperature is measured. So volume of a liquid, pressure of a gas, or resistance of a wire can be used to find out or to create a temperature scale. Then came this famous gentleman. these famous gentlemen. And they created their own scale, the Celsius, the Fahrenheit, the Reaumur, the Rankins, and the Kelvins. Degree Celsius, degree Fahrenheit, degree Reaumur, degree Rankin, and don't call it degree Kelvin, simply Kelvin. Now, if you are Celsius and you now know that you are going to create a thermometer, you are inventor of the thermometer, and you now know that I have to use property of a liquid. I have to use some physical property, and you decide on I will use the volume of a liquid, and then you find out a liquid which expands fast, does not stick on glass, and all these properties mercury have. Nobody is going to ask you those properties. You decide to put in mercury inside. Okay, I'll put a mercury. But then how do I call this as 500 or this as 400? From where do I get numbers? Now to get these numbers, we have to fix points. 2 points were fixed for all these scales. One was, since the most abundant thing on this planet is water, and without water there is no life, so we took water. Most of the things in thermodynamics are based on water, defined on water. Definition of 1 calorie is on water. Temperature scales are on water. So we find 2 very simple and very important processes of water which happen in day-to-day life. And what are those 2 processes that happen in day-to-day life?
Celsius and Fahrenheit.
Yes, bacha?
Celsius and Fahrenheit.
Melting and boiling points of water. These are the 2. Or freezing and boiling points of water. At some particular temperature, water freezes, becomes ice. At some particular temperature, water boils and becomes water vapor. I fix these points and I then give them random values. Remember, they were random values. Celsius called the melting point of water, the freezing point of water as 0 degree, and he called the boiling point of water as 100. So arbitrary numbers given to them, arbitrary numbers. Fahrenheit, on the other hand, called it 32 degree and 212. Reaumur called it 0 and 80. Rankine called it 460 C and 672. 212 is the difference. Kelvin scale was not based on this, so we'll just take this out. Kelvin scale was based on a different concept. But in Kelvin scale, the freezing point of water comes out to be 273.15. Very precise. And the boiling point is 373.15. Now they have the difference between the 2 scales, the difference between the 2 temperatures. In Celsius, 100. So what do we do? This is my first thermometer, filled with mercury. I mark 2 points. Tuck 0, tuck 100. Freezing point of water, boiling point of water. And in between these 0 and 100, I mark 100 equal divisions, 1 gas scale. Don't use your brains, scale 1 gas. Fahrenheit, 32, 212. In between, 180 equal divisions, 4 gas scale. That is how scales are created. Lower point, melting point of water, freezing point of water, melting point of ice, boiling point of water. And in between, we have assumed, which is not correct, we have assumed that the expansion is linear, but the expansion is not linear. And that is the problem with this scale, that the expansion of mercury between 0 to 100 is not linear. But we have considered it is fairly linear. So between 0 and 100, the temperatures that your mercury thermometer gives you are not exact, because they have considered that the expansion is linear, but the expansion is not linear. But it is fairly good enough to calculate. So now how do I create a thermometer? Oops, I have a small patla sa tube filled with mercury. I marked 0, I marked 100, and I have made 100 equal divisions. But how do I get this 0? So I dip this in water that is freezing, and I wait for some time, chill out, wait for some time, put this in a place where water is freezing. Now after some time, this thermometer and freezing water will come in thermal equilibrium. They will have the same temperature. Mercury will settle down and settle to a point. That point where mercury settles down, if it settles down here, I mark this point as what? I mark this point where mercury settles as what? I'm Celsius. I'm creating a temperature scale. I have taken this tube, this thermometer, and put it in freezing water. Mercury will settle down. It will settle down at some point. What do I call this point?
Melting point.
Yes?
Melting point.
No, I call this point as 0 degrees Celsius. I call this point as 0 degrees Celsius. So I mark this point as 0 degrees Celsius. So if this is my scale, if this is my mercury thermometer, I mark this point as 0 degrees Celsius. This is my melting point of water, which is 0, freezing point of water. Then I take this thermometer out and I boil and start boiling water in a beaker. When water starts to boil, I put this thermometer again back in the beaker. After some time, mercury will settle down. It will settle down at some point. What do I call this point? Let us say that it settles down here. What do I call this point? This is the boiling point of water, and on my scale, it is 100 degrees Celsius. Yes or no?
Yes, sir.
So I call this point as 100 degrees Celsius. That's it. I have created my scale. Now between 100 and between 0 and 100, I will mark 100 equal divisions. So these are 100 equal divisions that I have marked. 100 divisions I have marked. And my one division becomes equal to? One division becomes equal to?
1 unit.
1 degree Celsius. So this is 1 degree Celsius, this is 2, this is 3, and so on. Congratulations, your temperature scale is made. This is how temperature scales are made. This is how thermometers are made. This is how we call it. Thermometers are calibrated. If you mark something, mark the measurement, we call it calibration. This is how thermometers are calibrated. In case of Fahrenheit, what he did, instead of calling it as 0, he started calling it at 32 degrees Fahrenheit. Instead of calling that at 100, he called it 212 degrees Fahrenheit. Put it in freezing water, put it in boiling water, marked it at 32 and 212. And then in between them, he made how many equal divisions? 180 equal divisions. One division became equal to 1 degree F. Are we clear with this point?
Yes, sir.
Clear with this point? Yes. And that is how all scales are made. And that is why we have this phenomena that temperature on one scale can be converted into the other scale, because all the scales are based on the same property of the liquid. Mercury is the liquid that is used. The property remains same. The expansion of mercury remains same. Equal divisions are made. Therefore, the reading on any scale minus the lower fixed point divided by upper fixed point minus the lower fixed point is constant for all the scales. Do we all understand this? Do we all understand this equation? Have you seen this equation before? Have you seen this equation before, beta?
Yes, sir.
Yes? Yes or no?
Yes, sir.
So if I put Celsius, C minus 0 divided by 100. If I put Fahrenheit, F minus 32 divided by 180. If I put Kelvin, K minus 273.5 divided by 100. This Reaumur and Rankine are not used, so it may not be of any importance. These are three important, and if you solve them, you will get this equation. I hope all of you understand this. You must know this. If you know this, you can find out or convert temperature from one scale to temperature on the other scale. You can also create your own scale. You can also create your own scale. If I create my scale, so what do I do? How do I create it? I create a lower point. I create an upper point. In between them, I will create equal divisions, and that becomes my scale. The only thing is, if my scale is Aastik scale, reading on Aastik scale minus the lower point LP divided by the upper point minus lower point, that should be same as the other scales. If I have done this, I have created my own scale. So there can be questions based on this scale, and I'll give you an example of a question that can come from this topic. Have you solved any question based on temperature scales?
Yes, sir.
Okay, what type of temperature, what type of question comes? Okay, this is the type of question that you can expect. So I'll just show it to you. I'll send you this sheet, so you will be able to solve this question. These are pretty simple questions. This is question number 2. The freezing point on a thermometer, which is a different thermometer based on a different scale, is marked as 20 degrees. So lower fixed point is 20 degrees. Boiling point or upper point is 150. So we are now creating a new scale. Lower point is 120, upper point is 150. A temperature of 60 degrees Celsius will be how much? If the actual temperature is 60 degrees Celsius, on this new temperature, on this new thermometer, what would be 60 degrees Celsius shown as? Can you find it out? Any question that comes on the thermometer scale, any question that ever comes, sometimes the question is given in a different language. If it is given in a different language, it might be like this: a faulty thermometer. A thermometer has gone faulty. A faulty thermometer reads 20 degrees Celsius as melting point. This faulty thermometer reads 150 degrees Celsius as boiling point. What will it read when the temperature is 60 degrees Celsius? So this question that I have spoken and the question on your screen, they both are same questions. Do we understand this?
Yes, sir.
How do I solve this? We just use that equation and we are done. What is the equation that you use? The temperature on that thermometer minus the lower point divided by upper fixed point minus lower fixed point should be all constant. So if I call the temperature as X, X minus 20, 20 is the lower fixed point. This is the lower fixed point LP divided by the upper fixed point, which is 150. Upper fixed point 150 minus the lower fixed point, which is 20. That should be same as the Celsius scale C, temperature on the Celsius scale, minus the lower fixed point divided by upper fixed point minus the lower fixed point. From here, I can calculate the value of X, and the value of X comes as 90 degrees. So the thermometer will now read 98 degree in whatever, call it whatever unit. Am I clear? Do you understand this?
Yes, sir.
It's as simple as this. The same question could have been like this. The same question could have been like this. A thermometer is graduated in, it's marked in millimeters. It registers -3 mm when the bulb temperature in pure melting ice is 22. and the thermometer is in steam, boiling point. At a pressure of 1 atmosphere, the temperature in degrees Celsius when the thermometer registers 13 degrees. Okay, this is based on the pressure scale. Let us go on. Let us go back on the pressure scale. Let us do that first, and then let us come back. Now we have seen that whatever scale you make, you have to follow a simple principle. The simple principle being that temperature on the scale minus the lower point divided by upper point minus the lower point must be a constant. Now, based on this, you can create any scale. Now, these scales can be of three different types based on a volume of liquid, based on pressure of a gas. It can be based on the resistance of a thermometer. So, I summarize it. Length of liquid in a capillary tube. This is length basically stands for the volume. Pressure of a gas at constant volume. This is known as constant volume gas thermometer. Third one, volume of a gas at constant pressure, which is known as a constant pressure volume thermometer. Resistance of a platinum wire, which is known as resistance thermometer. Now remember, these all scales are either Celsius scales or Fahrenheit scales, because for Kelvin scale, we have a different phenomena, because we don't have to fix two arbitrary points. The Kelvin scale comes from a single point, probably. What is a single point? It also has 2 points, but that they are not the melting and the boiling points. What are those points? The 2 points, the 2 fixed points on the Kelvin scale. Any idea? Okay, not to worry, we will do it. So all these are based on the old concept of 2 fixed points, which were melting point and boiling point. There's a problem with the melting point and boiling point, and that is why we had this Kelvin scale. There was a problem with the melting point and boiling point of water. What was the problem? What is the problem? What are the problems with this liquid scales or this resistance scales? They have an inherent problem, and the inherent problem is there are 2 problems. First is these 2 fixed points, this melting point and boiling point, they're actually not fixed. They depend. On what it depends? It depends on pressure. Melting point and boiling point depends on pressure. If the pressure becomes if the pressure changes, the melting and boiling point of water also changes. And therefore, these thermometers will not give you the exact values even at different places. So if I am using the thermometer here in Bhopal and it is calibrated here in Bhopal, it will give me the correct temperature. But if I use the same thermometer on Himalayas, which is at a higher altitude, the melting and boiling point have changed slightly, and my thermometer will not give me the exact temperature. That is one problem. The second problem is we have made equal divisions, but the expansion is not linear, and therefore it will not give us the correct temperature. But considering all those probabilities, if I make a temperature scale based on melting and boiling point of water, I already know that temperature minus lower boiling point, lower point divided by upper point minus lower point must be a constant. Depending on the same principle, I can write this equation. And that equation comes from the same principle. What principle it comes from? Temperature on the Celsius scale minus the lower point on the Celsius scale divided by upper point minus lower point. So basically what I'm saying here is, if I have to draw it in terms of a graph, see, this is the graph. This graph is drawn between the length of the column L, how much mercury is there, and the temperature in degrees Celsius. Now, at 0 degrees Celsius, it will have some value. So this is length at 0 degrees Celsius. At 100 degrees Celsius, if I mark this as 100 degrees Celsius, there will be some length corresponding to it. I call it L100. So I have found out this L0 and L100. How did I find them out? I put them in freezing point of water, and I put them in melting point of water and boiling point of water, and I mark these points. And then I make equal division. So any temperature here, let me call this temperature as T. This temperature T will correspond to a length L. And then I can use a simple interpolation equation. I will not go into that equation. From here, you can find out the value of this T. From here, you can find out the value of this T in terms of L100, in terms of L0, in terms of L, in terms of 0 degree, and in terms of 100 degree. And the equation that you get is like this. Temperature on this, from this graph, will be X is standing for L, X minus X0 divided by X100 minus X0 multiplied by 100. Do you all understand this? Yes or no?
Yes, sir.
It comes from the linearity of the line. The line is a straight line. Now, if this was not degree centigrade, it was degree Fahrenheit, how will the equation look like in degree Fahrenheit? The same equation, how does it look like in degree Fahrenheit? Temperature on degree Fahrenheit, temperature on the Fahrenheit scale. How does it look like? So it will become TF, temperature on the Fahrenheit scale, will be equal to what? How will the formula look like? No one knows the answer?
X minus 32 by 180 into 100.
No. X minus X at 32 degree Fahrenheit divided by X at 212 degree Fahrenheit minus X at 32 degree Fahrenheit. That has to be multiplied by 180. Do we understand this?
Yes, sir.
I hope all of you are listening to this lecture.
Yes, sir.
Great. So I hope you understand the difference between the two equations, and they come from the same phenomena. This is the temperature in degree Fahrenheit based on the length of the liquid column. Correct? Shall we move ahead? Have you noted this down?
Yes, sir.
Okay. So here is a confirmation. Here is the confirmation of this liquid thermometers. For these liquid thermometers, this is the formula for degree Celsius that I was talking about, that we have already seen and understood. If I talk about gas thermometers, then there could be a constant pressure gas thermometer, there could be a constant volume gas thermometer, and for the Celsius, this is the formula how it looks like. Do we understand this? Yes or no?
Yes, sir.
Volume at temperature T minus volume at temperature 0 divided by volume at 100 minus volume at 0 should be equal to 100 degree multiplied by 100 degree. That will give us the temperature in degree Celsius. We understand this?
Yes, sir.
For Fahrenheit, it will just become 32 and 212. If it was Kelvin scale, now on the Kelvin scale, it looks like this. Do you know what is this VTR? The fixed points for the Kelvin scale. The Kelvin scale does not have two fixed points. One of these points of Kelvin scale is the absolute zero of temperature, 0 Kelvin. Do we know this?
Yes, sir.
Okay. The other fixed point, now I cannot take melting point as the other fixed point. I cannot take boiling point as the other fixed point because they depend on pressure. So I go for a point which does not depend on all those things. It is a point which happens in a particular condition at a particular pressure at a particular state, and that is known as triple point of water. Do we understand this?
Yes, sir.
Triple point of water. And then they gave this triple point of water the value as 273.16 Kelvin. Do you know this?
Yes, sir.
So for any calculation or any temperature on the Kelvin scale, you have the formula which looks like this. For a formula on the Celsius scale, the formula looks like this. Temperature on the Celsius scale is P minus P naught divided by P100 minus P naught multiplied by 100. But for the Kelvin scale, it becomes 273.16 multiplied by P divided by pressure at the triple point of water. Do we understand all these formulas that I've written?
Sir.
Right? Temperature scales we are talking about. Then we have this resistance thermometer, and since you have already done this, you must be aware of this formula. Resistance of any wire at any get temperature T is R naught into 1 plus alpha into T. You know this formula? This alpha is known as,
Linear constant.
this is known as temperature coefficient of resistance. The same formula, the same formula is applicable for resistivity. Rho at temperature T is rho at temperature naught into 1 plus alpha into T minus T naught. Do you know this formula?
Yes, sir.
Actually, this formula comes from this formula. This is the actual formula for resistivity. From resistivity, we can convert it into resistance. So this alpha is a constant. And then from there, you can have this formula coming for the temperature in degrees Celsius in terms of resistance of a wire. Temperature in degrees Celsius will be R minus R naught divided by R100 minus R naught. Temperature on the Kelvin scale will be coming in this fashion. Am I clear with this?
Yes,
I hope everybody is noting this down. Because if you are not noting this down and you are wasting your time, I hope you will utilize your time elsewhere. Now you can go on and solve the problem that we were discussing in the first case. Thermometer is graduated in mm. It registers minus 3 mm when the bulb of the temperature is in pure melting ice and 22 temperature when the thermometer is in steam at a pressure of 1 atmosphere. What is the temperature in degrees Celsius when the thermometer registers 13 mm? So this is in terms of millimeters. You have been given the length of the liquid column, not length of the liquid column. It is given in terms of the pressure of a gas. You can always convert from the formula that you have understood. You can find out the temperature when the thermometer is registering 30 mm. It could be 13 mm of liquid column. It could be 13 mm of liquid pressure. I hope you know that pressure can be set in terms of mm. So how do I calculate the temperature in degrees Celsius? The given pressure or given length minus pressure or length at 0 degrees Celsius divided by pressure at 100 degrees Celsius minus pressure at 0 degrees Celsius multiplied by 100, and you will have the answer. Do we understand this? Do you understand how it is done?
Yes, sir.
Similarly, for problem number 4, the temperature coefficient of resistance of a wire is itna. At 300 Kelvin, the temperature is itna, the resistance itna. What is the resistance of wire? At what temperature the resistance of wire will be 2 ohms? You can easily use the formula that I've already given. These are the type of questions that normally come in the exam. If it comes on the temperature scale, hardly I have seen any question in the temperature scale. But since it is a part of your course, it's important that we do it. So we have finished this topic here. The temperature scales are done and dusted with. In the next class, we will be moving on to probably thermal expansion, and then we'll probably move on to calorimetry. So thermal expansion would be probably coming in the next class, and we'll try to wind it up in one class or so. Well, that's it from my end. I hope you find this class interesting. I see one or two of you not being interested in the class. I hope better sense will prevail. If you are not interested in the class, well, you are free to leave and enjoy your time elsewhere. I have no problems with that. But if you're in the class, let us utilize your time in since you are wasting a year of your life in giving JEE, at least utilize it. That would be good. Chalo. I'll pause this class here and I will see you in the next class, that is tomorrow. Thermal expansion we'll be discussing. I'll be sending this sheet and I hope that you get this sheet. Take care. Have a nice day.